thank you all for being here also at 8:30 in the morning, an unheavenly hour to go and listen to some technical stuff. So particularly this slot, it's going to be a little bit more technical than the average content what you will find, over here. So what I'm going to be talking about is a comparison between different segment routing data plane encodings. So there are like many different ways of comparing the different segment routing technologies we have. This is just one of them. Is it the only one? No, there are like multiple ones. But I think this one is important because it provides you with some objective data on what is the bandwidth impact upon your network potentially. So let's have a look. So if you look into the market needs, initially we had like our traditional technologies, and they work very well. So we actually had like LDP, we had RSVP, policy-based routing, to actually steer a packet from the ingress of your network towards the egress of your network. Now, with the current needs for services in the network, which are very highly dynamic, which are very, many devices, because we have this Internet of Things, we have like millions of devices potentially. It becomes very complex for a network to do the right thing. So the current architecture as we have today, it has been working very well for the last 15 years. It will keep on working very well for the next 10 years. But the reality is, we need to do something. That's where segment routing came, into the place. So segment routing initially was invented to simplify the architecture, to reduce the state within the network, and to make everything easier from an operational perspective. So, and the way we were doing that is we're actually, upon the packet itself, the data plane packet, we actually are encoding information, instructions on how the network should handle this particular packet. And these instructions are called segments. And that is where, how the way we actually encode those segments, up on the wire, there are like different mechanisms on how to do that. And it will be upon you as an operator, you as a network, person, to decide which one is going to be best for you going forward. So you have like a few choices here. And you need to make the right choice, for your network. So some choices will be better for like greenfield environments. Other choices, you may want to take, from a segment routing perspective, will lead you to a technology which is more suitable for a for brownfield kind of networks, where you have like a mixed kind of environment, where you don't have the greenfield, experience. So in essence, so what do we bring with segment routing? So we route our packets through the network based upon segments. And each segment is either an instruction based for a location instruction, like send it to somewhere, or a service instruction, like do something with a particular packet, send it through a firewall, for example, or through some sort of an optimizer. So these segments, you actually have like different sizes. You can actually go for 32-bit segments, or you can go like 128-bit segments. So what you are doing in your network infrastructure, you route your packet, you switch your packet through the network based upon looking at these segments. Now, of course, if you want to encode a 32 bits, if you want to route your packet upon a 32-bit segments, you will use different forwarding technology than you will use if you encode your segments as 128-bit, instructions. So, but the key important thing for segment routing is there is no flow contained within the network, so no per flow state contained. The segments, the instructions are actually distributed by your routing protocols or by a controller. And also on top of that segment routing, you can actually also add like some metadata instructions telling where the packet came from, about the subscriber or about the virtual slice, for example, by adding a network services header. So you can actually do that also. And then a very important element here is also, so in some of the cases you will use like an NSH header, but that is not always necessary, because if you use like bigger segments, like the 128-bit segments, for example, you have the potential to add some context within the address itself. So in that case, if you do that, you don't really necessarily need an NSH if you did some very simplistic things. So going forward. So in the next 18 minutes, I'm going to be comparing here apples with apples. And actually, I sort of like make it look like this, because that is the way most people look into this. They look into segment routing as like very different kind of things, and how do we compare them? It will, from the high level, it looks different, but from the inside, so this is maybe like an apple and an orange, but in general, it's fruit. Yeah? So that's what I'm going to be comparing it to. So in this case, I will be comparing doing segment routing based upon 32-bit segments and segment routing using 128-bit segments. So initially, when segment routing came out, it was, as a goal, and the goal of it was to simplify the MPLS forwarding within the network. So again, initially, it was really a simplification. One of the troublesome parts of MPLS is that you actually were forced to use LDP, and LDP within the network is an additional protocol, and it gave you like a whole lot of complications. You don't really want that. What you want is that all of your segments are completely in full sync, with your IP prefixes, and everything is, distributed as quickly as possible. And that is what we're doing with segment routing. So in this case, we do not distribute our labels, our 32-bit labels, by using LDP, but we actually use our routing protocols like OSPF, ISAS, or BGP, or we actually use a controller to distribute the segment itself. There is like an IETF draft on that. One of the benefits of using 32-bit segments is you can completely reuse the complete forwarding plane, the forwarding mechanisms in hardware from MPLS. The way the MPLS forwarding actually is programmed is slightly different, but you can use exactly the same kind of forwarding mechanisms in ASIC. So that's pretty good. It's very ASIC friendly. So the principle used is we have like 32-bit segments, whereof in MPLS world, we have like 20 bits, which actually is the label, and we have like 12 bits, telling some additional information about the label itself. So another benefit by using this mechanism is the overhead what you impose is relatively low. So we will see in some of the other segment routing technologies we have, the overhead tax is slightly larger, but at the same time, it gives you like some additional benefits. It's actually pretty mature. Many people have been using MPLS forwarding for a very long time and have lots of operational experience with it, so all of that can be retained. It is relatively secure, and all the security implications are are quite well known. And the technology sweet spot for using 32-bit segments, if you have an MPLS underlay already, is that it's very simple to introduce. So there's not really a particular flag day to start introducing this. You can actually run this at the same time with your MPLS if that is what you want. So perfect for brownfield kind of environments. How does it look like on the wire? It looks like this. So we have our original packet, what you see in the black here on the bottom. We add on top our segments, so our sequence of MPLS labels. And each label, what you see in blue, is like 32 bits. That's what we have. So that's relatively simple, and very low overhead, based upon the goodness of your packet. So people found that a very good idea, and they said like, okay, that is really good, Gunter, but imagine if you have like, if you don't want MPLS, if your network infrastructure is IPv6, what do you do then? Do I have to install MPLS for doing this segment routing thing? And then a few very smart people, they came up with like, okay, why not use like, native IPv6 for a segment routing infrastructure? And then they came up with like, then they start thinking like, but how do we program in that case our sequence of segments to go through? And then they looked like, okay, what sort of technologies do we have available? Oh, yes, we have like source routing. So if you do source routing, with source routing, you actually, add a new segment, an extension header in IPv6, you can do that. And in there, you actually add a set of hops the packet will have to traverse through. And that actually is very similar to what we were doing with 32-bit segments. So it's a sequence of segments. Now, in this case, if you use IPv6, your segment is not going to be 32 bits. It's going to be much longer. It's going to be the size of an IPv6 address. It's much bigger, 128 bits. So if you do this with IPv6 underlay, then your segments are going to move from size from 32 bits to 128 bits. It's bigger. At the same time, because it is bigger, you also have the benefit that you can actually add a little bit of more context about what the packet actually is about. You can actually give a bit more information. So that is something you have available. But it comes at a cost. Because if you do that, if your instructions are bigger, then also the header overhead, what you will impose, is going to be bigger also. So you need to be aware of that. So it's pros and cons. And what is best for you will be based upon how you look into your network. So other artifacts here is that this thing is for an IPv6 only data plane at this point in time. And you also need to look into hardware considerations here, because traditionally source routing in an operator network was not really promoted. Most of the time source routing was actually a security risk, and as a result, because often if you do source routing, then what happens on the router is it receives the packet, it sees the source routing packet, it will punt it to the CPU, and it will not use ASIC forwarding. So something actually has to change there. So from that perspective, it tends to be less ASIC hardware forwarding friendly than the MPLS version, because the instructions are bigger. It's a fact. So from a security perspective, so the interesting element here is that the semantics mix of using an IPv6 128-bit instruction is sort of like mixed location and the context. So you need to be aware of that also, which is a new kind of a thing, because depending upon the place you are in the network, your destination address either will point towards context information or it will point towards location information. It's a new thing. So that is something you need to be aware about also. Oops, I'm too far away. Ooh. Okay. Yes, whatever. It's okay now. It blocked me for a while. So if you look into the encoding here, then this is what we have. So we have the original packet here again. On top of that, we add our IPv6 segment routing header. And here we have first our 40 bytes traditional IPv6 tunnel header. Underneath it, we actually have our segment routing extension header, source routing, which is 8-byte fixed header most of the time. 4 bytes of them are mandatory. And then we have our different segments, what we have here. So, but in this case, segments are going to be, instead of 32 bits, going to be 128 bits. And then, because we mix context with location, we may want to use, this is optional, an additional security header in here also. And if we actually are using it, it means 40 bytes extra. So how does it look like? So let's do it like this. Oops. So here, what we have on the left-hand side is our original packet. It goes to the provider edge router, where the segment routing IPv6 header actually is imposed. And as a result, we actually add some bits and bytes here. We add our 40 bytes tunnel header. We add our segment routing header, which is variable in size, 8 bytes fixed because of the extension header, plus x times 16 bytes for each segment. And then we may want to add actually our HMAC, our security header also, which is going to be 40 bytes. Again, that is optional. So 2 weeks ago, it was in the IETF, where it actually was kind of investigated what is the impact of the overhead, what is the bandwidth overhead. So if you look into packets being of about 500 bytes, then the percentage of overhead of what you have for SRv6 is so with 3 sits, which is relatively common. It means overhead is going to be 56 bytes. So it actually means for short packets, which is a common internet size nowadays, because of the services we have, it means a little bit more than 11% overhead of what you have. So you need to be aware of that, because bandwidth doesn't come for free. So if you compare that with the 32-bit segments, then this is where we are right now. So both of them actually switch your packet through the network. So the 32-bit segment routing, again, it is not MPLS, it is segment routing because we're not using LDP. For the 128-bit segments, don't confuse it with classical IPv6 because it is not IPv6. We're doing segment routing because we're routing upon 128-bit segments. It is not IPv6, it's different. So now the question is okay, now this is really good. We like the fact that we have 32-bit segments using an MPLS underlay. we have like 128-bit segments using an IPv6 underlay. But what if, can we actually use 32-bit segments on a native IPv4 or IPv6 underlay? Yeah, of course we can. And this is not something new at all. It has been actually out there for quite a while. So we have been able to do MPLS over UDP over IPv4 and IPv6 networks. So it actually goes under the radar. A lot of people, and it's very hardware-friendly, and that is where we are. So what we are doing is we encapsulate our 32-bit segments in a UDP header. And the UDP can actually write over traditional IPv4 and traditional IPv6. So again, this actually is very nice again, because we don't really have like any flag day necessary at the operator. The operator can use MPLS, he can use IPv4 native, can use IPv6 native, and we can use our 32-bit segments. So how does it look like? It's actually very similar to the 128-bit segments for segment routing v6. But things are named a little bit different here. So the first thing we have is we have our outer IP tunnel header, which is going to be about 20 bytes for IPv4 and about 40 bytes for IPv6. Then we actually have our UDP header, which is going to be 8 bytes. And then we have our sequence of segments, which in this case, because we do 32-bit segments, it's going to be like, each segment 32 bits. And then again, we can actually do our network services header insertion for providing extra context, if that is necessary for your infrastructure. So if you compare them next to each other, segment routing v6 and then segment routing over UDP, this is what we have. It looks very similar. And both can actually write over IPv6 native, but the one over UDP can go over MPLS and can also go over IPv4. But if you look into the headers, how it is constructed, it is very similar. So the IPv6 encapsulation header on IPv6 front will be the IP tunnel header in the segment routing over UDP. Same size approximately. For the SRH extension header, which is going to be 8 byte, for the SRv6, we're going to have like an 8 byte UDP header. And then we're going to have like our 128-bit segments underneath it, and then we actually have our optional NSH header. So if you look into the different IPv6 use cases, so the IETF, it does many things, and some of them actually are very useful. Yeah, party. So they actually have like a document describing, the use cases for segment routing in an IPv6, environment. And actually, both of these options are fully approved, and they support 100% all of the use cases actually documented here. So with respect to bandwidth overhead, so in the interest of time, I'm going to go a little bit quicker here. So if you look into the SRv6, we already talked before. So if you have like 3 segments the packet needs to go through, and if you look into like, for a classic 500-byte payload packet, then for the SRv6, because of the larger segments, we're going to end up with about like 11% overhead. In the segment routing over UDP, we're going to be ending up with about like 4% bandwidth overhead. Again, it doesn't look like a lot, but bandwidth doesn't come for free. You need to be aware of it. Then the last step here is what we call like, the seamless segment routing. So this is a combination of these. So this is something what you can do with like 32-bit segments at this point in time. So this actually means that you have the ability to go from an MPLS data plane to an IPv4 data plane to an IPv6 data plane. So this actually is a perfect environment if you're not greenfield, but if you have a network already right now with like, which consisting out of different data plane encodings. For example, your core is MPLS, your data center is classical IP, which is a very normal environment. Then what you can do with the seamless segment routing is go MPLS over the backbone, but then go segment routing over UDP in your data center. And that is where we are. So within the Nokia environment, for example, that is what we are using in our infrastructure. So we are using the variant of like seamless segment routing, where we can switch between different data plane encodings, but we actually are using at this point in time 32-bit segments. We can go to the other one also if there is like really a need. Until now, we haven't really seen a very good reason to do that, to go to 128 bits. So again, deployment scenario for this one is like really brownfield networks. So if you have a mixed environment, this is actually the perfect way of going there. So concluding at the end, going apples to apples, and I see a very happy chairman here. So if you compare these, then I sort of like divided them up in two different buckets. So one going from 32-bit segments, which actually is like segment routing over MPLS and segment routing over UDP. So this actually brings you can actually keep using what you have right now. So if you're using MPLS, IPv4, IPv6, you can keep using it. There is no need for a forklift upgrade. It actually works seamless across different kind of data planes. The bandwidth overhead, what you impose, is relatively small. It's ASIC friendly because we have been using it for years, and it has very well documented security properties. Going for segment routing v6 with 128-bit segments. It's a very innovative way, which actually is very useful if you have like a greenfield IPv6 network. It gives you the benefit that you actually have the capability of imposing context upon the address itself. So that is something new, something cool, what you can do. And the other thing what I would like to make you aware about is that because the property of doing special behavior upon very long addresses, it has ASIC implications. So you need to be aware of that also. So by that, I'm actually going to hand it over again to my chairman here. And